Welcome to my YouTube channel. Watch, like, share and comment.
So welcome to today's lesson, and in this lesson we shall be looking at the alkaline earth metals. I request that you subscribe to the channel so that you don't miss other exciting lessons. The objectives of the day: by the end of the lesson, each and every learner should be able to state the physical properties of alkaline earth metals, the chemical properties of alkaline earth metals, and finally state at least a few uses of alkaline earth metals. So we look at the members of the alkaline earth metals, and like you can see from what we have in the diagram here, the alkaline earth metals are usually made up of a group of elements, and for the first 20 elements we'll just be looking at barium, then magnesium, and finally calcium. Note that these elements are found in group 2 of the periodic table, and they are usually referred to as the alkaline earth metals. The reason for their name is because most of these metals are found naturally from the earth. The physical properties of these metals. When we speak about the physical properties, we shall be looking at the atomic radius, and like you can see from the diagram, the atomic radius of these elements increase as we go down the group. See that the size of barium, then we have the size of magnesium, and finally the size of calcium being largest among the three members. Why then should we have an increase in size? You know that the atomic number of barium is 4. What does that mean? If we were to draw the barium atom, the structure of the atom, with 4 as the atomic number, we will have the first energy level having only 2 electrons, and then the second energy level will also have 2 electrons to make up for the 4 elements. Remember that from the atomic number being 4, the electron configuration of barium will be 2:2. So the first 2 electrons in the first energy level, and the second 2 electrons in the second energy level. So if we were to draw the structure of magnesium, which is the second member, it will look like this. So that now we have additional energy level. We will have another electron here, because the second energy level, of course, will have 8 electrons, and then another electron there, another electron to make up to 8. And then now we will have the last energy level for magnesium, like that, now having only 2, having like, yes, sorry for that, having 2 electrons. So if you compare the size of, barium, let's look at the size of barium. You note that the barium had only 2 energy levels. So the fact that it has 2 energy levels and magnesium has 3 energy levels means that the size of barium will be smaller than that of magnesium. If we were to draw the atomic size of calcium, it will look like this. We'll just need to have calcium here. We write calcium. Then the electron configuration of calcium is 2, 8, 8, 2, meaning that it has 4 energy levels. So on the energy levels of magnesium, we will just add an additional energy level to now accommodate the extra 2 electrons for calcium, which will be there and maybe there. And then now the second energy level, the third energy level for calcium is also complete. So we complete this one with more electrons, so that now we have the first energy level having 2 electrons, the second energy level with 8 electrons, the third energy level with 8 electrons, and then the last one having 2 electrons. So if you compare the size of calcium, that of magnesium, and that of barium, you will note that as we go down the group, starting from here, barium, the size increases because we have these 2 energy levels, this one 3 energy levels, and this one 4 energy levels. For that reason, the size of the atoms in group 2 elements increase as we go down the group reason due to the increase in the number of energy levels. So we look at something different, the melting point. Because of the same size, we have barium being comparatively smaller than calcium and magnesium. For that reason, barium has very small particles. The size of its atom is very small. And because of that, the particles are able to pack more closely and form a substance or a structure that is hard compared to calcium, which has a bigger size atom, and as a result, the particles of calcium are not able to pack more closely. So for the same reason, due to the small size of barium particles, which are able to pack more closely, we find that the melting and the boiling point of barium will be higher than that of magnesium, and that of magnesium will be higher than that of calcium. So anytime you are explaining the difference in melting and the boiling points of alkaline earth metals, you explain using the size of the atom. The size is very small, hence can be able to pack more closely, resulting to a substance having a higher boiling and melting point. And the next thing we look at the electrical conductivity. And when we speak about the electrical conductivity, you note that the electron configuration of barium, for barium, it's 2, 8, is to 1, sorry, is to 2. That one for magnesium, it's 2, 8, 2. Sorry, for barium it's different. For barium is 2, 8, 2 is to 2. And then we finally have the electron configuration for calcium, which now is 2, first write calcium, 2, 8, 8, 2. So when we speak about the electrical conductivity, every time electrical conductivity is facilitated by the free electrons, which are usually in the outermost energy level for metals. So comparing the 3 metals, barium has 2 electrons in the outermost energy level, magnesium has 2 electrons in the outermost energy level, and calcium as well has 2 electrons in the outermost energy level. As a result, all these 3 elements are good conductors of electricity, and their electrical conductivity is the same due to the fact that they have the same number of electrons that are available for electrical conductivity. And then we look at the next which is the first and the second ionization energy. And what is the ionization energy? Ionization energy is basically defined as the minimum amount of energy that is lost by an atom when they lose an electron in gaseous state. And in this case, let's look at, we use magnesium to explain the ionization energy. This is now magnesium atom that looks like this. We use magnesium as an example. Magnesium having 12 electrons, that is, its atomic number is 12, and therefore its electron configuration is 2, 8, 2. So when we have the atomic structure looking like this, and the configuration look like this, that means that if we take magnesium and then we want it to lose, remember that we are saying that it is in gaseous state, it will lose an electron like this, which is also gaseous, plus 1 electron. When magnesium does like this, loses the first electron, we say that it has undergone the first ionization energy. Then we have the second ionization energy, whereby now the ion that we have here will lose the second electron like this. We have magnesium again, but then in this case it has a positive charge and it is still in gaseous state, giving us magnesium. After losing the second electron, it becomes positively charged 2, and then still it is gaseous, plus it has now lost another electron. When it does like this, we call this one now the second ionization energy. So we have the first ionization energy that resulted to it losing only 1 electron, and then again we have the second ionization energy leading to the loss of the second electron. And at that point now we have the magnesium ion. What does that mean? Remember that when we say that an atom is losing 2 electrons, they are not lost simultaneously. No. The atom first loses the first electron, and that is when we say that it has undergone the first ionization energy, and then now again loses the second electron to give us the second ionization energy. And then the next question that we need to ask ourselves is, between the first and the second ionization energy, which one is higher? Remember that this is energy that is measured in kilojoules per mole. That means that the first ionization energy is usually less than the second ionization energy. Why? When the first electron has been lost, the other electrons are held more firmly, more strongly by the nuclear charge, and therefore getting the second electron from the outermost energy level will require us to have more energy than getting the first electron from the same atom. And every time now, the second ionization energy will always be higher than the first ionization energy. Should we go to atoms like aluminium, which have even the third ionization energy, the explanation will be the same, that the third ionization energy is higher than the subsequent second ionization energy and then the first ionization energy. And the reason for that is each and every time an electron is lost, the remaining electrons are held more firmly, and therefore getting them will be automatically be more hectic or more difficult than when we were losing the first electron. I hope that point is noted down. So we get to the chemical properties of the alkaline earth metals. And to begin with the reaction with water. I'll use an example of magnesium. If you take magnesium and then you put it into a beaker, this is magnesium ribbon, a small size of magnesium ribbon like this, and then you drop it into a beaker containing water. A reaction will take place. If this is magnesium, a reaction will take place. And what will be formed? Every time a metal reacts with water, the products that are usually formed is magnesium. So we have metal plus water. We always form metal hydroxide plus hydrogen gas. So let's look at an example now using magnesium as our metal in this case, plus oxygen plus water. So we have magnesium, which is a solid, reacted with water, which is a liquid, to give us magnesium hydroxide plus hydrogen gas. We check whether the equation is balanced. So we have one magnesium on this side, one magnesium on this other side. The reactant side we have 2 hydrogen. On this other side we have 4 hydrogen. That means that the number of hydrogen is not balanced. So we can maybe think of balancing with like a 2 here. If we put a 2 there, we will have 4 hydrogen. And then what about the number of oxygen? The oxygen is, we have 2 on the reactant side and 2 on the product side. So the equation is now balanced. If you are going to write the equation now for barium reacting with water, nothing different will change. You just come here, we will have now in place of magnesium, we will have barium. Let me use a different pen. We will have just barium, and then we also replace magnesium here with barium. You know that the balancing will still be the same because we are using the atoms or elements that are within the same group, that is group 2. The thread will also remain the same. If we were to write the equation now for calcium reacting with water, because we just need to come here and have calcium and calcium here to give us calcium hydroxide and hydrogen gas. Next, we look at the oxygen, that is reaction of alkaline earth metals with oxygen gas. And we begin with magnesium. For magnesium, we say that every time a metal burns in oxygen, the product that is formed is a metal oxide. So we have magnesium, which is a solid, reacted with oxygen gas, it will give us magnesium oxide, which is a solid. We have to write that equation and check whether it's balanced. We have one magnesium atom in the reactant side and one magnesium atom in the product side. We have 2 oxygen in the reactant side, and on the product side we only have 1 oxygen. So we need to balance that by thinking of maybe having a 2 here So if we put a 2 there, we have now 2 oxygen on the product side and 2 on the reactant side, but you note that having a 2 here also affects the number of magnesium. So we also put a 2 here so that now we have 2 magnesium on the reactant side and 2 on the product side, 2 oxygen on the reactant side, and 2 oxygen atoms in the product side. And you note that no chemical equation is ever correct without it being balanced. If you are to write the equation for calcium reacting with oxygen, I hope now you can be able to get the trend. Pause the video and try to see whether you are able to do that. Welcome back. I hope this is how you wrote it. You just need to replace where we had calcium and replace it with where we had magnesium in the first place. So we have now calcium and the equation is automatically balanced. The same will be for barium. If you need to write an equation now for oxygen and barium, you just need to come here and replace what we had as calcium with barium, and the equation is automatically balanced because we are still working with atoms or elements that are in the same group. The next thing that we look at is reaction with dilute acids. And reaction with dilute acids, we have 2 types of acids, the organic acids and the inorganic acids. The organic acids are like the malic acid, the ethanoic acid, and so on and so forth. But for our reaction, for our practice in this particular lesson, we will use hydrochloric acid and maybe sulfuric 6 acid, and then maybe nitric 5 acid. We can check now how magnesium will react with these dilute acids. Magnesium, it is a solid, will react with hydrochloric acid, which is aqueous, to form magnesium chloride, which is aqueous, plus hydrogen gas. Hydrogen gas will be liberated. In our previous lessons, we have seen that metals react with acids to give us salt and hydrogen gas. So the salt that is formed in this case is magnesium chloride, and then we have our hydrogen gas being formed there. So this is the case. We just need to check whether the equation is balanced. We have 1 magnesium in the reactant side and 1 magnesium in the product side. We have only a single hydrogen on the reactant side and 2 in the product side. So in balancing, we can maybe think of maybe having a 2 here, so that now we have 2 hydrogen on this side, the reactant side, and 2 hydrogen on the product side. Then chlorides. Now we have 2 of them because these 2 affect both hydrogen and chloride ions. So we have 2 chloride, and then we have 2 on the product side, and our equation is balanced that way. We might now need to try out the same, but now with calcium. When we speak about calcium, of course, we are still working with elements that belong to the same group. Therefore, we just need to replace what we had there as magnesium with calcium. And then again, we come here on the product. We change that one so that we have calcium chloride plus calcium chloride plus hydrogen gas. You note that the balancing remains the same because the elements that are in question in this case belong to the same group. So if you are to write the equation for barium with hydrochloric acid, nothing different will change. Just need to replace the calcium in this case with your metal, and the metal in this case is barium, and the equation is still balanced. You can pause the video and try to write the equation for these metals with nitric 5 acid. Welcome back. We can check and try to see whether your answers are correct. We look at the equation for magnesium with nitric 5 acid. So we have magnesium, which is a solid, reacting with nitric 5 acid, which is aqueous, to give us magnesium nitrate, and it's aqueous, plus hydrogen gas. Remember, we said that every time a metal reacts with an acid, there is production of hydrogen gas, and then we'll also have a salt. So in our case, in this case now, we have magnesium nitrate as our salt, and then we have hydrogen gas. Sorry, this is not water, it's supposed to be hydrogen gas. Hydrogen gas being liberated. So to have calcium reacting with nitric 5 acid again, we just need to replace, as usual, replace the magnesium in this case with calcium, so that now we have calcium, and then we have also calcium on this other case to give us calcium nitrate and hydrogen gas. Okay? Writing the equation for barium with nitric 5 acid again, we don't need to struggle, students. We just need to come here and just replace the calcium, and the calcium in that case with barium. Then we have barium nitrate plus hydrogen gas, and it's done. So now, next, we look and see whether we can still be able to do the same for the first 3 members of the alkaline earth metals reacting now with sulfuric 6 acid. So what do you expect? What should be the product that is formed when calcium reacts with sulfuric 6 acid? I hope you said calcium sulfate. Well, that one reacting between the sulfuric 6 acid and magnesium, we will form magnesium sulfate and hydrogen gas with barium sulfate plus hydrogen gas. And in this case, I just want us to have an example of magnesium, and then you can try others in your own time. So we have, magnesium is a solid reacting with sulfuric 6 acid. This is the formula, which is aqueous, to give us magnesium sulfate, an aqueous solution plus hydrogen gas. And is the equation balanced? Let's check. We have 1 magnesium in the reactant side and 1 in the product side. We have 2 hydrogen in the reactant side, 2 in the product side. We have 1 sulfur in the reactant side and 1 in the product side. We have 4 oxygen atoms in the reactant side and 4 of them in the product side. And then in that case, we can say that the reaction is, or the equation is balanced. So reaction with barium, students, we just need to change where we have magnesium. We have magnesium here, and then we just write our barium. The equation is now balanced. Come on, you can see that? Yes, and then to react calcium with sulfuric 6 acid, now what do? We replace again where we have barium with what? With calcium. So we have calcium and we have calcium. And the equation is just balanced normally. Now, there is something I need to mention here. Reaction between calcium and sulfuric 6 acid stops almost immediately after you drop calcium into a beaker containing sulfuric 6 acid. Why? Remember that calcium sulfate is insoluble. So the moment you release calcium into sulfuric 6 acid like this, we have a beaker, and then we have here sulfuric 6 acid, and then you now bring in calcium. This is now your calcium metal. The reaction stops almost immediately because the reaction, or there is production, there is formation of calcium sulfate around this around the calcium, and that calcium sulfate, which is insoluble, prevents formation or prevents further reaction. As a result, the reaction stops. Yes, are we there? Next, we look at reaction of these same elements with chlorine gas, and it is very simple. We will use, for example, calcium, which is a solid, reacting with chlorine, which is a gas, to give us calcium chloride. It is a solid. What do we need to check? Whether the equation is balanced. 1 calcium in the reactant side, 1 in the product side. 2 chlorine atoms in the reactant side, 2 in the product side. The equation is balanced. So how do you write now equation for magnesium and magnesium with chlorine? You just need to change. Where we had calcium now, we replace with magnesium. We have magnesium, and the equation is balanced. Pause the video and try to write the equation for the reaction between barium and chloride. Are you there? I hope that you just replaced magnesium, so that now we have barium and barium, and the equation is already balanced. We now have barium reacting with chlorine to form barium chloride, and this is now our salt. To get it right, you can mark it correct if you got it. Next, we look now at the uses of alkaline earth metals. So, like you can see from the screen, magnesium ignites easily in air and burns with a bright light, and for this reason it is used in the formation of fireworks. Then we have Grignard reagents, which are organic magnesium compounds. They are very important in chemical industry. Then we have calcium metal, is used as a reducing agent in preparing other metals such as thorium and uranium. We have then, everybody has ever seen an aeroplane. So the metals that are used to make aeroplane must be very light to at least ensure that it has a higher capacity. So for that reason, we usually make an alloy made of magnesium and aluminium. This alloy is very light and it's used in making of aeroplane parts. Then we have magnesium hydroxide is used in the manufacture of anti-acid tablets. You have heard of people complain of their stomachs, and they get tablets. After some time, they say that they are feeling well. That is because we use magnesium hydroxide. Remember that magnesium hydroxide is a base, and every time you hear people complain of heartburn in their stomachs, it's because of production of a lot of hydrochloric acid in their stomachs. So how do we do that? We neutralize the acid in the stomach by use of a base, and our base in this case is magnesium hydroxide. Caution, don't just consume magnesium hydroxide in the laboratory. You just take it as a medicine from a pharmacy. Why? The magnesium hydroxide from the laboratory is usually prepared for experiments and not for medicinal purpose. Then we have calcium nitrate is used as a fertilizer. And then we also have, it is also used as an alloy agent for aluminium, barium, copper, and lead, and magnesium alloy. That is calcium. All right. Thank you for watching the lesson. I advise that you subscribe to the channel and share this clip with your friends so that together we build an ocean of chemistry. Thank you.